And guys, we are starting. Let me share the live link with the people, with the good people of Discord. Copy pasting it here. Let me just remove the embed. Going through FSDP right now. Okay guys, let's go through this. The goal for today will be to understand a bit more about the fully sharded data parallel. It might be a big overlap between this and Megatron and deep speed and everything we went through before. I made some YouTube videos about these topics, but maybe there's some special terminology and FairSec is using FSDP. And having said that, I think it's worthwhile to just understand a bit better how this works. Also, just because I'm confused, like I'm currently training a 615 million parameter model using FairSec, and for some reason it's eating up almost both of my RTX 3090, which means 48 gigabytes, which is by any measurements like not the expected number. Like at worst, if we even had 24 bytes per one parameter, that would give us around 16 gigabytes of VRAM. And so I cannot currently explain why so much memory is being eaten up with the training. So let's get some understanding of FSDP and we can take it away from there. Okay, so let's see. There is some diagram here. Let's check it out. PyTorch DDP, which is distributed data parallel. Opt sharding, which is probably optimizer sharding. And then there is the FSDP. Max model size in billions. Number of GPUs. Okay, so apparently if you have 8 GPUs, then the max number you can train is with FSDP is around whatever this is, 20 billion parameter, let's say, and then that number grows. And again, FSDP is better, much better than PyTorch DDP. Again, this is we are missing out on deep speed in some of these zero techniques and stuff. So this is by no means state of the art in this, but let's just understand it. Training AI models at a large scale isn't easy. Aside from the need for large amounts of computing power and resources, there is also considerable engineering complexity behind training very large models. At Fair Engineering, we have been working on building tools and infra to make training large AI models easier. Our recent work in areas such as intra-layer model parallelism, pipeline model parallelism, optimizer state plus gradient sharding, and mixture of experts is just part of our work to make training advanced AI models for any number of tasks more efficient. Okay, FSDP is the newest tool we are introducing. When was this, by the way? This was back in 2021. Okay, it charts on an AI model's parameters across data parallel workers and can optionally offload part of the training computation to the CPUs. As its name suggests, FSDP is a type of data parallel training algorithm. Although the parameters are sharded to different GPUs, the computation for each micro batch of data is still local to each GPU worker. This conceptual simplicity makes FSDP easier to understand and more applicable to a wide range of usage scenarios compared with intra-layer parallelism and pipeline parallelism. Okay, so it's a type of data parallel training algorithm. Although the parameters are sharded to different GPUs, the computation is still local. Okay, let's see what they mean by all of that. Compared with optimizer state plus gradient sharding data parallel methods, FSDP shards parameters more uniformly and is capable of better performance via communication and computation overlap during training. With FSDP, it's now possible to more efficiently train models that are orders of magnitude larger using fewer GPUs. It's been implemented in the FairScale library, which we use in the background with FairSec, and allows engineers and developers to scale and optimize the training of their models with simple APIs. At Facebook, FSDP has already been integrated and tested for training some of our NLP and vision models. Okay? Is there an actual paper behind this? Okay. let me skip here just to see how it works, how to use it, next steps. Okay, there is no paper. This is just a kind of the report, the technical report. NLP research is one of particular area where we can see the importance of efficiently leveraging compute for training AI. Last year, OpenAI announced that they had trained GPT-3, the largest ever, blah, 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 taken 335 GPU years to train GPT-3, or the equivalent of 1,000 GPUs working continuously for more than 4 months. I think in reality, then they had like 10K V100s. So that means divide 4 months by 10, you end up with what? 2-3 weeks of training? Ideally, if there are no crashes. Obviously in the early days, probably they had a bunch of failures. Okay. For example, typical data parallel training requires maintaining redundant copies of the model in each GPU, and model parallel training introduces additional communication costs to move activations between workers. FSDP is a relatively free of trade-offs in comparison. It improves memory efficiency by sharding model parameters, gradients, and optimizer states across GPUs, and improves computational efficiency by decomposing the communication and overlapping it with both the forward and backward pass. It produces identical results as standard distributed data parallel training and is available in an easy-to-use interface that's a drop-in replacement for PyTorch DDP. Can enable scaling to trillions of parameters. Okay, how it works. In standard DDP training, every worker processes a separate batch, and gradients are summed across workers using an all-reduce operation. While DDP has become very popular, it takes more GPU memory than it needs because the model weights and optimizer states are replicated across all DDP workers. One method to reduce replications is to apply a process called full parameter sharding, where only a subset of the model parameters, gradients, and optimizers needed for a local computation is made available. And the implementation of this method 03 has already been popularized by Microsoft. The key insight to unlock full parameter sharding is that we can decompose the all reduce operations in DDP into separate reduce, scatter, and all gather operations. Okay, so basically, let's see what they're saying here. So let's say all of them have like a single chunk of data. That's why I'm parsing this A, B, C, D. So that's 4 different micro batches. They process them, then they communicate, and so B sends data to C, to A, and C sends it to A, and D sends it to A, and so it's a fully connected graph there. Everybody sends everything to everyone, and so you end up with all of them now have all of the data. That's why I'm parsing this, and that's done using the all reduce. But maybe that's not the case. Let's just understand what this plot is telling us. Here we have reduce scatter, so we additionally chunk up the data, and then we have here A0, B0, C0, D0, and this guy has A1, B1, C1, D1, and then here, and then here, and then we do all gather to end up with A, B, C, D. So I'm not sure what happened here. Let's understand. So all reduce is as a combination of reduce, scatter, and all gather. Aha, okay, this is equivalent. So you can kind of decompose this into this, okay? The standard all reduce operation to aggregate gradients can be decomposed into 2 separate phases: reduce, scatter, and all gather. During the reduce scatter phase, the gradients are summed in equal blocks among ranks on each GPU based on their rank index. During the all gather, the sharded portion of aggregated gradients available on each GPU are made available on all GPUs. Okay. So I guess this guy now has to send this to the other ones, which is less data than if it had to send all of the gradients to them 3. So you can reduce the communication overhead, I guess. Let me just think for a second. Yeah, there is a lot of details to decompose this. So for now, let's just treat it as a black box. I'm certain this is not super hard to parse, but for now, let's just continue. We can then rearrange the reduce, scatter, and all gather so that each TDP worker needs to store only a single shard of parameters and optimizer states. The figure below illustrates standard TDP training top and FSDP training bottom. Okay, model shard, forward, local, backward, local, all reduce, and then update weights local. Forward local, backward local, all reduce, you gradient sync, and then you, okay, this is DDP. Assume we have 2 GPUs. You basically have like a copy of the model on both GPUs, and then you do forward, backward on both of them independently on separate pieces of data, and then you send the gradients to each other, and now it's as if you had all of the data yourself, and then you just apply the gradients. On the other hand, let's see what FSDP does. So you have a model shard. You do the all gather, and then n layers forward. Excuse me. Backward local, all gather, reduce, scatter. A comparison of standard DDP and fully sharded data parallel training. In standard DDP, a copy of the model is present on each GPU, and sequence of forward and backward passes are evaluated on only a shard of the data. After these local computations, the parameters and optimizers for each local process are shared with the other GPUs in order to calculate the global weight update. You don't share parameters and optimizers, you just share the gradients. And then using gradients, you can reconstruct the parameters. So I'm not sure what they're saying here. In FSDP, only a shard of the model is present on the GPU. Then locally, all weights are gathered from the other GPUs. By means of an all gather step to calculate the forward pass. This gathering of weights is then performed again before the backward pass. After that backward pass, the local gradients are averaged and shared across the GPUs by means of a reduced scatter step, which allows each GPU to update its local weight shard. Okay, so as far as I can tell here, all gather of the gather weights, and then reduce scatter gradients, whereas here is just gradients. To maximize memory efficiency, we can discard the full weights after each layer's forward pass, saving memory for subsequent layers. This can be implemented by applying the FSD wrapper to every layer in the network, with reshard after forward set to true. So basically, as you do a forward pass through this particular shard, you can disregard it because now you don't need it for the next layers. So that's what they do. They discard the weights after each layer's forward pass, saving the memory for subsequent layers. But at one point, you still have the peak, right? At one point, you still have all of the weights. So like, what does it even matter if you just remove those? You still have the same peak, right? You can't reduce the peak, which begins at the beginning of the forward pass. Reshard after forward. Let's see whether this one is mentioned in FairStack. Probably not, because it's a part of FairScale. Don't reshard parameters after forward pass. Or do reshard parameters after forward pass. So it's false, which means you reshard after forward pass. FSDP config. Okay. Interesting. Let's see. Don't reshard. So this is the distributed training config. And again, so that means we will be sharding after, sharding the parameters after forward pass. So let's just see here, FSDP, CPU offload. By the way, we use this FSDP enable rep in our training, so very much worth a while to make sure this is the case. If memory efficient FP16, then we assert that we set this to true. Get the group config. Okay. These are just snapshot codes. A ton of snapshots. Let me just do one thing. Let's go here. Let me just delete all of this. And now let's see what we got here. When DB runs, let's just delete the when DB runs as well. Move to trash. Let's now see. So that's the only two places where this is called. There is a setting here, and then there is a setting here which sets up the FSDP. Okay, let's go back to the reading. So in pseudocode, FSDP forward pass for layer in layers, all gather the full weights for layer I. Oh, okay. This actually makes more sense. So you do, when they say shard, you don't take the layer I, you take the piece of the layer I. So that means before you do the forward pass through the layer I, you gather those weights and then you do a forward pass and then you disregard. So that means at the peak of your memory usage is basically gonna be whatever the size of the layer is. Okay, so that's very much different to my mental model just before reading this pseudocode. That's why pseudocode is super useful. It's incredible that in 5 lines I got a better understanding than like just going through this whole thing. Now we can parse this here. So for n layers, each time we do all gather to form the layer, then we do a forward pass, and then we repeat that 10 times. Once we are done, then we do the backward, and it's the same logic. All gather, backward, all gather, backward, n times, combined with reduce scatter. So you first do all gather because you need the layer, then you do the backward through that layer, and then you do the reduce scatter, which syncs the gradients. Okay, makes sense. So all gather, backward, discard, and reduce scatter. How to use FSDP? There are several ways to use FSDP in large-scale AI research. At this time, we offer 4 solutions. Using in language models, setting DDP backend to fully sharded, which is exactly the setting we are currently using. So if we go here, if we go to our long JSON, we can find FSDP being set here, fully sharded for DDP backend. Okay. CPU offload offloads the optimizer state and FP32 model copy to CPU, combined with optimizer CPU atom. I don't think we're definitely not using this. We're not using the CPU offload, and then combined with optimizer CPU atom. No reshard after forward increases the training speed for large models and is similar to 0 Stage 2. Okay. Other popular options, FP16 update frequency. This just tells you how many how many batches you have to calculate the gradients for before you actually apply the weights. So like the accumulation, the gradient accumulation, number of steps. Checkpoint activations for recomputation, and then offload activations continue to work as normal. So we don't do this, we do this, and we set reshard after forward. See the first tutorial for instructions on using FSDP to train a 13 billion parameter model on 8 GPUs or on a single GPU with FSDP plus CPU offloading. Interesting. Let's just take a look at that one. Okay, but this would be probably super slow to make this practical. We can skim through this after we are done. Using FSDP in computer vision models supported in this framework and tested on RegNets architectures. Layers like batch norm and ReLU are seamlessly handled and tested for convergence. Use the following options to enable FSDP. Auto setup, true, sync on type, AMP type. This is automatic mixed precision type, PyTorch. Okay. Using FSDP from PyTorch Lightning. Using the library directly from Fairscale. Okay, so just replace this with FSDP, and then you just call sharded module. There is the model wrapping. In order to minimize the transient GPU memory needs, users need to wrap a model in a nested fashion. This introduces additional complexity. The auto wrap utility is useful in annotating existing PyTorch model codes for nested wrapping purposes. Model initialization. Unlike DDP, FSDP does not automatically synchronize model weights between GPU workers. Let me just see. For this wrapping, we already have that in the main code here. If we open up train, if we open up in FairSec, if we go to the train.py, let me just find the train.py. Where are you? Train script, looking for FairSec CLI directory. FairSec CLI. Here it is, train.py, and then FSDP wrap. Here it is. That's the syntax for wrapping the build model into FSDP. Okay, model initialization. Unlike DDP, FSDP does not automatically synchronize model weights between GPU workers. This means model initialization must be done carefully so that all GPU workers have the identical initial weights. Optimizer settings. Due to sharding and wrapping, only certain types of optimizer and optimizer settings are supported by FSDP. In particular, if a module is wrapped by FSDP and its parameters are flattened into a single tensor, users cannot use different hyperparams for different parameter groups. Mixed precision supports advanced mixed precision training with FP16 master weights as well as FP16 reduce and scatter. may converge only if full precision is used. In those cases, additional wrapping is needed to selectively run parts of a model in full precision. Okay. It's open source, and early users have tried it and contributed. Being a purely data parallel training scheme, FSDP has the greatest potential to be general in supporting a wide range of AI algorithms. I don't know what they mean by purely data parallel training scheme, because they also have model parallelism. Obviously, they shard the model. Like, what do they mean by purely data parallel? Okay, there are some auto-tuning algorithms they're working on. More scalable inference and model serving is an important use case. Refactoring continuing to modularize FSDP and its core components is equally important to newer and better features. Nice. Okay. We went through that blog. So it's just a mix and mash of the techniques we've seen previously as well. Nothing super fancy there. I'm still confused. One thing that we need to double check is we need to understand where are we sharding our model, or are we... Yeah, let's see why we are using so much memory for the 615 million parameter model I'm currently training. So that's completely not clear. Okay. Why are we using the amount of VRAM? Why are we using the amount? Okay. Okay, guys. Let's skim through that other README we found up there, and then I want to run the data preparation stage in the background. Let's see. Recent work by Microsoft and Google has shown that data parallel training can be made more efficient by sharding the model parameters and optimize their state across data parallel workers. These ideas are encapsulated in the new fully sharded data parallel wrapper provided by Fairscale. Compared to PDP, produces identical results as PyTorch CDP. It's still synchronous, shards parameters and optimize their state across data parallel GPUs. So it's literally like 0.2 from DeepSpeed from Microsoft. Faster than PyTorch CDP because the optimizer step is sharded and the communication can be overlapped with the forward pass. Enables training 13 billion on 8 GPUs. Fully supported in FairSec. Okay. Not compatible with AdaGrad, AdaFactor, LAM. Well, we are mostly using Adam and AdamW either case. Depends on flattening the parameters. So models that currently require FP60 no flattened grads may not be supported. How it works. And I guess we've seen that blog. Whoops. Example usage illustrates how to train a very large language model with 13 billion on one GPU. Nice. By offloading parameters and optimizer states to CPU, or innate by fully sharding the parameters and optimizer states across GPUs. These examples use the Wikitext 103 dataset for demonstration purposes. But in practice, a much larger dataset will be needed. The optimizer step happens on CPU. You'll need 32 gigabytes of GPU and 256 gigabytes of system memory. Okay, so that means you still have to have a ton of RAM. I only have 64 gigabytes of RAM, and I have 24 gigabytes on a single GPU. I have 2 GPUs, so I have 48. If you have less system memory, the 6.7 can be trained with 128 gigabytes. We use the CPU from deep speed. Okay, so you still need to install deep speed. The command will take 5 minutes to start training, during which time it will appear to be hung, since randomly initializing 30 billion weights can be slow. Okay. Let's see this. Fully sharded, FP16, CPU offload, tokens per sample, bed size, architecture, example output. Okay. 30 billion parameters on 8 GPUs. Sharding enables training the same 13 billion without offloading the parameters to CPU. However, without CPU offloading, we'd only be able to fit a batch size of 1, which would cause training speed to suffer. We obtain the best performance on 8 GPUs by combining full sharding and CPU offloading. Nice. Okay. Let me just see whether there is any other resource. Why did this come out only in 2023? Okay, so it's now part of PyTorch 2.0 release. This is definitely something we need to read before we start training, just to allow us to easier understand and debug stuff and performance issues. We can put this on our reading list for the next couple of days. We can skim through these two. Okay, let's kind of put these on our reading list. Let me just put it somewhere here. Reading list. It's highly likely they've explained FSDP better in this paper with more detail than they've done in the blog there. Okay. Let me now quickly kick off the data preparation stage. While we are waiting for it, we can continue doing other stuff so that we are not blocked. So let's go to prepare data script. Let's grab the, let's go to the config. Okay, so what we need here is we need to put both Flores 202 here and also push the new data. Let me just see quickly. Okay, so prepare data train corpora, prepare extra configs. So this is what we want to do. We want to run this one. Filter data root path. Let's get our filter data root path. Here it is. Filter new. Copy the path. Let's go to prepare extra configs long JSON. And let's put it here. And then we have train primary config path. Okay, this looks good. Let's go to prepare extra config and let's run it. Prepare extra config, kick off the run. We go through the files. We grab the gzips. We do some asserts. And for that direction and that corpus name with that source, we add the mapping to the new file, which is filtered file. And then we open up the config that contains the data, the raw data, and then we just fill it in. And then we just hit F5 here and we have train corpora YAML. Okay, train corpora YAML. Where do we save it? Here it is. So again, it just contains paths for each direction. We have different data sets for that direction, and we have the the filter data link there. Okay, so that's good here. Now let's add for validation. For validation, we need, let's add Flores for validation. In this case, we can actually we can directly dump it here because we just have a single data set. So let's do that. Again, train corpora. Let's go to train corpora. And let's just copy the format. So this is the format that's expected. Copy this. Go to prepare data. Validation. Okay. Direction. Dataset. Whoops. Wait, what did I do? Okay, looking good. Okay, the only issue is we might need more directions, right? We have to figure out still which directions we want to cover. Maybe it makes sense to create an automatic way to configure this. Let me think for a second. How will it know where? Okay, let's just do it like this. This is Flores CO2. We want to support, for example, for now, let's see, data, eval data sets, on dev. Let's go with these. Let's just grab these. This is the first direction. And then let's copy the path. This is going to be the source. I'm not sure what it's going to complain because it's not gzip. If so, we can then easily make sure that our data is in gzip format, but I doubt it will complain. The second direction we're going to grab is this one. Let's grab it here. Oops. Actually, let's first grab the actual name of the direction. Okay. Again, Flores CO2, and then source and target, and then we grab the directions there. Copy path, Turkish, copy path, this one. Okay. Looking good. English, Russian, Turkish. Okay, let's just test this works. And if it does, then we can maybe change. Maybe we can just use some languages which are more related than Turkish, English, and Russian, which are all pretty much from different language families. I'm not sure about user then, but yeah. Partition null. Output directory is gonna be process data new, creatively named, and then everything else will be what? Local launcher. Okay. Local null. 15 jobs per job array. Okay, why not 16 there? And then pre-processing. I don't want to touch that. Vocab, we're gonna leave that as it is as well, because if I recall correctly, Well, actually, no. Let's change this one. Should be, we renamed this one, right? We renamed this one. So let me just find the actual name. Here it is. Okay. Save that. Same for the target. Whoops. Save that. We're done with vocab. Let's go to dedupe. Dedupe neither. That looks good. Sharding default. That also looks good. And I think we're ready, guys. We can kick this off. Process data. Let's call it just new for now. not the most creative name in the world, but it will work. Okay, so let's see if this works with this format. If it works, then before triggering the actual run, I want to, again, as I said, pick different set of languages. Something that will make sense, that we can actually run and be confident that we can train. Okay. Let's kick off the prepare data run. I also need to make one note. Optimize the data prepare stage, batch it. We might need to add batching logic to the data prepare stage if we're running locally. Similar to what I've done for a couple of stages like binarization and filtering. Okay. Kicking this off. We can set no arguments here because everything comes from the prepare data config. Let's go. Here is the training config. And we also have, let me just see, corpora, train and validation. Okay, it seems it worked. It seems it worked here, but let's see whether the lack of gzip might mess with it. Get the data sets for fold. We are now in the train fold. We keep on repeating, and then we go for the validation fold. Okay. Language direction, corpus, grab the source, and pack it into the dataset. All good. We are good. The last ones will be the validation ones. Yes. Let's retrieve that back. Check the files exist. Save, read only, and we can now run. Let's go here and then validate. Let me just see whether validation will work with this type of files. We pass in data sets, and then here okay, and then we run. Waiting to get to here. As you can see, it's starting a ton of processes. So that's something I want to handle. I want to make sure we are batching these processes as opposed to starting like a trillion processes. Validating data sets, count lines. Okay, now I'm confident this will work. Both for gzip as well as for regular files, because count lines works for both of those. That much I know for sure. Okay, I'm stopping this. I'm stopping the whole run, and I'm going to modify the logic here inside of validate such that we batch this if we are running with a local launcher. So let me explain what I mean by that. Let's go to binarize and see how we've implemented it there. So if the launcher partition is none, then we are running locally, not on Slurm, and then we can, oops, why did I indent this more than I need? And then in that case, we can run some batching logic. Let me show you how we can do that. Go to validate, go back here. Just do the following. If it's none, that means we are running locally. Otherwise, keep the same logic as before. Otherwise, just keep this logic. Okay, on the other hand, if we are, if it's none, then just hardcode batch size here to like 16, and then for I in range 0 through length of data sets, we want to move by batch size steps, and then we want to do what? We want to chunk data sets batch is going to be data sets like this, and then we pass those data sets here, and then we run the validation only on those, if that makes sense, guys. So we are effectively batching this and fixing this for local runs. Okay, this should work. Let's test it. And then I can literally just let this run and not have to babysit it like the last time. If you were here on the stream, we had to babysit this prepare data pipeline. Now we won't have to do that anymore. Okay, hit F5, go inside validate, hit F5 here. Here we are. We enter here. We grab the first 16 data sets. We create this, and then we hit run. So now this is going to trigger only 16 processes as opposed to being like 300 or whatnot. And this is now just much more manageable. So that means if we go and hit F5, this is going to run. Let me just hit F5 again. Let this run to completion. As you can see, only 16 and much more reliable. And now we go back and we grab the next batch, and again, much more reliable. And we can just now keep this running until we are done, and it will not fail like the last time. Okay, at least that's what I think will happen. Because there isn't a wait here. A wait statement forces us to wait until the whole batch is done, and only then do we grab the next 16 ones and we run it as well. Okay, here's the next one. So that looks amazing. That looks amazing. We can go back to prepare data, and we can fix retrieve data as well. So I guess similar logic will be here. Just a second. We have two more tasks after we wrap this up. One is to figure out why we're using the amount of VRM that we're using, and also the second one is to help new joiners to onboard on this project and what can you start playing with, etc., etc. So let's see here, what happens here. We go through the data sets, and for default and language direction, we append. So this is a default dictionary. And then we create, a bunch of jobs here. For each of the folds. Wait, just a sec. So the data sets will be, okay, fold and language direction. So we go through the data sets, we grab their directions, and we end up with fold direction. We ignore those, and we just append the data set. This should be, okay, always small. Only a couple of data sets will be here, but this will be a huge list. And because of that, we want to batch it here. Okay, it's going to be the same logic, guys. We want to go and wrap this up in a for loop and just see what's the launcher. Same logic as with validate. So if the launcher is none, then we do certain type of logic. Otherwise, we keep it as it is. So if we are here, processing config will always be the same. I assume output directory will also always be the same, but we need to run over these. I'll just hardcore the batch size here. Exactly, Copilot is reading my mind. Okay, and then grab a batch here, and instead of data jobs, we pass in the batch. Looking good. We do this, we wait, and then we go on to the next iteration. Looking good. I think this is all we'll need to do. Potentially, we might need to change the output directory. Let's see whether that's indeed the case or not. Let's see. Retrieve data. Retrieve data receives that. And then on the run, we grab the iteration value, we grab the data sets. Where do you write to? We build the output data, concatenate the files. Where does one write to? When this run is over, what happens? We just retrieve those, but where are those dumped? Where is that specified? let's quickly see this. Metadata, data sets. Bash pipe fail. Concatenate the files. This one will just run the command output file. Okay, here it is. I could have just used output directory like this. Let me see. Retrieve data, and the only place where it is used is here. So it specifies this. Okay, so we don't have to change that because each of those subsequent jobs will also have different direction, language direction, and different fold. So we can just keep the same output directory. This is good. I think we've handled retrieve data as well. Let's go to the main pipeline, which is prepare data, and let's handle the next ones. So for vocab building, we don't have to do anything because we are reusing the SPM200 tokenizer. For dedupe sharding, we'll probably need to do something. Let's just see what exactly. So what happens here? The good thing here is we're not messing this up for people later who want to run this on Slurm. Let me just double check something on my... Okay. Dedupe sharding. Get the number of shards per language direction. Let's see what this one does. Well, actually, this one is fairly fast and will not be submitting any processes, so we're good. The only problematic pieces are when we are doing schedulers. This is all good and nice. This is all good. Eval. We should now have eval, right? We should have eval. Okay, yes. Flores will be eval for us. So eval datasets. If eval datasets is none, then we do this, which will not be the case. Okay, so then crossfold is true for us. So that means, okay, we end up creating a ton of these jobs. And then we create, again, this is going to be similar stuff here. Everything we need to do is here. We just need to batch this, guys. So let's just, and I'm just copy pasting that, hard coding that batch size everywhere. Maybe we can just create it a config, like a local batch size or something that can be used if you're running locally. Yeah, for now, let's just leave it like this. So let's copy from here. Let's go to here, copy the same logic. Go to dedupe sharding, do it here, go here, put else, copy paste the same code, everything remains the same in the else branch, which is assuming we're running on Slurm. Otherwise, again, we just do for I in range 0 through whatever the length of this job is, batch size, and then we basically create dedupe sharding jobs batch, and then we pass in the batch instead of the jobs, and everything else should remain the same, but let's just double check that's the case. Can anything go wrong here? I doubt it, because the only thing we're doing is basically we're just making sure that we're kind of building. It's almost like implementing like a barrier. We wait for the 16 processes to finish processing, and only then do we continue on to the next patch. Victor asks how more difficult it is to stream and to work than just to work. To be honest, I think it might be even easier to stream and to work, because it's helping me when I think out loud, and when I'm trying to explain it to others, I'm also helping myself. And I'm also putting some higher amount of accountability on myself when I'm streaming and filming myself for so many hours. So it might be even better and easier. I don't know. I'm also used to it a bit because of YouTube channel. If you were just to get started, it might be a bit more difficult, because there is a couple of things to think about, and yeah. For me, I think it's better. And it's a fun experiment. And I think some people are finding it useful as well, so that's cool. Okay. And the final logic is the binarization here. I think I've already implemented this, and let's see. Do we need to do this? I think we do. So in this case, usually schedule doesn't retrieve anything, right? Usually when we ran schedule, okay, we get the validation results here as well. Yes, I made a small mistake. It's a good thing I noticed. So here we actually need to extend the results as opposed to retrieve the results. Right? Otherwise we have a bug. So this is just a list, and then instead of allocating every time de novo, we want to basically extend the list with the newest results. And now these two are equivalent. Same thing for the retrieve data. This will retrieve the data. If we do it like this, we'll basically just end up retrieving just the last batch of data sets as opposed to the whole thing. So let's create it. Let's build it. Put it here. And then just extend. Whoops. And I'll have to unfortunately stop this because we had a bug. But at least we know now it works. Again, retrieve data, validate, we create the results here, then we iterate. This makes sense. And for retrieving, again, outside of the loop, we create a list and then we just extend. And finally, we retrieve back the retrieve data sets. So that's that. And then what else? Dedupe sharding. Let's see here. Probably the same error. Yes. Again, we need to define a list outside here. And then we need to actually extend here. And now this is equivalent. And the final step is the binarization step. That actually helped me realize that I had a bug, because I actually wanted to remove this, but I realized the other examples were actually wrong. So we again go through the batch. We grab the source train shards, the target, and then the same for eval. We run. We grab these. So here, because there are multiple results, I just have a bit different logic. We extend down there. So we extend here. We extend, And then if I rename this now, then I'm gonna mess it up, I think. Yes, we need to do this at the very end. Again, this is just a bug here. We need to do this after the very end of the for loop. So we keep on extending so that we have the equivalent lists, and then we just rename it such that we can reuse it later on down below. Okay, guys, I think we've handled the whole pipeline. Binarization, dedupe, validate, and retrieve data. All four seem good. So now let's kick off the run again. Potentially we can increase the batch size to make it go faster. I'm not sure how that's gonna reflect on the results, whether we have any crashes, but let's give it a try. Maybe it works faster, because yeah, maybe not, maybe it does. Hit run again on the prepare data pipeline, and let's go and enter validate and wait until this finishes. So now we're gonna have 32 processes. Let's see whether that's gonna mess it up or not. Let's wait just for a single cycle to complete, and then we can continue. By the way, this is not coffee, for those of you who are wondering. Just some herb tea. That's kind of like a Russian coffee or something. Cicoria, I think, something like that. I'm not sure what's the English name. I don't even drink coffee. Waiting for this. The next step will be to figure out why we are wasting so much memory when we are training. Completely puzzles me still. Okay, so far looking promising. It might well happen that because we're running this in Python, the tasks are blocked until the CPU core is free. Okay. Looking good. Oh, we are already done with 64. This definitely seems to be faster. With 32, it's going way faster. We don't even have to go through the validate stage anymore. We can just comment that out to make stuff a bit faster, because we've already done the validation for all of our data sets, so it's good. Let's put the breakpoint for the retrieved data, and then we can wait for that to finish. Until then, we can go to parsec go to the train script, CLI train script, and let's find why are we eating up so much memory. I'm gonna set the train local. Let me just see whether I didn't mess up anything there with the configs. So we have fp16 atom stat. That's good. Disable validation. For now, that's good. VenDB, all that is good. Yeah, this is good. The number of max tokens is 2048. So now go to train. Kick off the run. And see when do we load. When does the loading happen? I guess after the model is built. Already after we exit this context here, this context manager, on line 116, we already have loaded everything to CUDA. That's the hypothesis. If that's the case, then we can dig into it and see why we are getting the amount of memory usage that we are seeing. Okay, so NVIDIA SMI. It's already 4,000. The interesting part is, before we even start loading the models, we already have a ton of memory wasted. I mean, obviously, I'm using some of this to drive the monitors and stuff. But before the program starts, one is 0 and the other one is around maybe 2 gigabytes. So that's the baseline I have. So let me stop this and rerun it from scratch and show you what I mean. So if I stop this, let me just expand this a bit. Clear. Let's see, the NVIDIA SMI output is, as I said, almost 0 here, 2.5 gigabytes for some reason. I'm not sure what's eating up my GPU so much. I'm not sure what's the best way. If you guys know any way of understanding exactly what's eating up my GPU, let me know. If not, I can just quickly Google. Okay, none of these answers are satisfactory. I'm not looking into how much GPU I have. I'm looking what's eating my GPU, same as what Task Manager in Windows does for like CPU. Exactly. Okay, let's try this one. Nothing. Okay, not super informative. So what's this process? query process on Ubuntu. Using its PID. How to get process details from PID. OBS. Oh, okay. Okay, that makes sense. I'm streaming. I forgot about it. So OBS is currently responsible for the memory consumption we are seeing. So OBS is taking around 2-3 gigabytes because I'm streaming. Okay, that makes sense. Nice. Having seen that, let's see where, when, at which point does the memory skyrocket. So if I hit run, this is still low, and then at one point it's not. So let's see when that happens. Let's just add the watch. I'm gonna put the watch here on the side, spine the watch exactly. I'm gonna put this on the side here of the screen. You won't see it for now, but I'm gonna show you as soon as there is something interesting happening. Okay, continue, call the main. It might very well happen that after this line we get some usage. Okay, not still is all good. We spawn 2 processes. Let's hit F5, torch multiprocessing spawn. Okay, now it's loaded. Okay, let's put, I made a mistake. I wanted to stop here. Hit it again. Let's see where this happens. 2 processes being spawned, but my GPU is still the same. Okay, now before we even start, this is my consumption. 5 gigabytes here, 2 gigabytes here. So that means we added roughly 2 gigabytes per GPU of something by just doing this logic here. Call main, spawn. Okay, that's interesting. And then here, could it be that this is the responsible thing, not the spawning itself? Let's see, let's hit the run again. Oops, I'm not running the right file. Let's run this one. Hit the 5. Okay, still reasonable. Okay, here we finished in Stopes we finished the validation step. Let me just quickly make a interrupt routine here and wrap this up. Okay, train, and then validation. Fair enough. And then we add a bunch of these, and then we enter here, and then we start chunking, and then let's see whether this extension works. Okay, let's run this. And while that's running, let's go here. Set device. What is causing the explosion? Probably this one. Obviously this one. But what exactly? Init process group maybe? Oops, let me just open Stopes again. Okay. And here we have 16. So let's hit F5 again. Run. And wait to see whether this is really extended with 16 new results. Okay, init process group, NCCL, distributed rank. Highly likely that's what's happening. Or maybe some CUDA stuff that can be flushed. I suspect it's this. Hit F5. Whoops, again. Here we are, extended. Nice. Now I can just put a breakpoint here and hit F5 until this wraps up. We don't have to watch it anymore. Let's see here. This is stuck for some reason. Let's see why. Why are you stuck? Because maybe the other process is blocking it. Wouldn't be the first time. Yes, of course. Hit F5, enter, hit F5, and let's see, hit F5. I don't see any explosion there. After all reduce, yes. Okay, this one messed up one of the GPUs, and now with the second process, once I do this, let's see. So let me show you here. 5 gigabytes now here, 14 megabytes. After we run this, we're gonna get 2 gigabytes plus. So let's run this. This is the second GPU, and let me show you. Here it is. So this operation here is causing the overhead. So let's just quickly dig into it and understand why this is happening. Let me remove. No, let me just rerun train. Let's just understand what's going on there. Hit F5. Okay, hit F5 again. F5 again. Okay. Enter here. Come to here. Let's see whether both of these are okay. Run here. What does all reduce exactly do? So we have torque zeros, we create 1 0, we put it to the GPU, and then we do all reduce to perform performs a dummy all reduce to initialize the NCCL communicator. Let's try and step into this if possible. Okay, we are now inside of all reduce. We passed in a 0 tensor. That's on CUDA. Reduce operation is sum by default. Group is none. Async is false. Reduces the tensor data across all machines in such a way that all get the final result. After the call, tensor is going to be bitwise identical in all processes. Check a single tensor. If it's not an instance of tensor, okay, if rank not in group, if group is none, return false. Okay, if tensor is complex, which is not, then we create the all reduce operations. Reduce up is just an enum time delta. Difference between two. Okay, let's go back here. Group is none. Get the default group. If not initialized, get back the process group and CCL object. Check whether this process was launched with torch distributed elastic. The existence of the torch elastic run ID environment variables is used as a proxy to determine whether the current process was launched with torch elastic. This is a reasonable proxy since torch elastic run ID maps to the rendezvous ID, which is always a non-null value. Okay. Let's retrieve back the world, and then default PG, we call all reduce on this object using this tensor and using the opts from above, setting it to sum, and then if sync, otherwise wait. So I guess this is going to trigger, this is going to trigger the second process to advance. All reduce. Okay, both are here, I guess. Yes. Both are now initialized. Okay, let me then Google one thing. Why is this so intensive in terms of memory? Why do I have to pay so much? Torch. And this is apparently in C++ or something, so let's try. Let's try this again. Let's stop this. Stop. Rerun. In the meanwhile, let's just run this. It was too fast. Hit F5, enter here, hit F5. Let's go to the second job. Let's go to the second process, enter, hit F5. Get into the all reduce. Interesting. It's already increased. Just by the very nature of calling this, it's already up. Look at this. The GPU is already up here with memory, even though we haven't done anything. Trying to F11 here doesn't work. even though I'm fairly confident that my train script, just my code, uses false. So it's not just my code. We can enter other Python code, but we're not doing that because what? Okay, this is now blocked because I had a bad order of operations. We run. Enter here. Okay. Let's see my memory. Still all reasonable. So memory looks good. And then once I enter here, it just explodes. Let's see. Enter. Explodes. Completely explodes. And then this one, same. Just entering this very function does something. So we probably trigger a lot of different things. So let's just Google that. Torch distributed. Okay, so the reducer will create gradient buckets. Gradient buckets that I guess will be used to do the all reduce, right? That's the thing, guys. It creates the gradient buckets so that we can communicate. So we get 2 gigabytes. Why? 650 million, let's assume, even with FP16 2 bytes. That's 1.2 billion. 1.2 billion bytes or 1.2 gigabytes. I'm trying to understand why this number. But the thing is, we don't even know what's the size of the model yet. How can they know? We didn't even instantiate the model yet. Okay. Let's try and see what they say in FairSec. Let me just share this with people who were following this work. Turns out this dummy all reduce increases my GPU VRAM consumption by 2 gigabytes on each of my 2 GPUs. Currently, they allocate gradient buckets in the background, but not clear why 2 gigabytes, given that the model hasn't even been instantiated yet. Weird. So before I even start, I think it's kind of clear. I don't want to mention the OBS because of streaming. Let's go to, let's quickly go to here, FairSec issue. Let's see whether people mention bucket as a word. Oh, a ton of buckets. There is a ton of buckets here apparently. Let's see whether gradient bucket scopes it down a bit. Okay. Okay. Why did anyone mention gradient bucket here? Okay, let's see what else. Valid NLL loss went up. Slower speed with distributed multi-node training. There is a known bug. Let's quickly see what's the config for our distributed data parallel. I mean, not for DDP, but for distributed compute in general. So if we go here, go here, go here, distributed training config, rank, NCCL backend, port number, gradient as bucket view. slow-mo. Pipeline. Zero sharding, FP16. Memory efficient. Huh. Nothing super clear here. Nothing obvious that this would be causing these. Can train customized model multiple GPUs. Does anybody mention slow? Okay, this was the NCCL bug. Let's try NCCL slow or NCCL memory. How many do we have? A ton. Memory. Memory overhead. Okay. Let me just note this. Let me just note this somewhere. Running all dummy, all reduce, bumps up VRAM usage by 2 gigabytes per GPU. Why? For building the actual model. Okay. Now that we've seen that this happens, let's go and see how much the model actually allocates itself. Okay, we definitely can't enter that one. Remove this, go to train, go to FSDP, rep, exactly, hit F5, hit F5 again, and here we are. Okay, I'm observing my memory consumption, and after we enter here, nothing changes per se entering the context, but let's see what happens when we run the rep. Okay, nothing happened because we still haven't pushed the model to the, I assume we haven't pushed the model to GPU. Let's see after trainer. Nothing happens there as well. Where do we see model being called? Nope, 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 nope. Let's go here. Okay, something is weird. We bumped it up at one point. Aha, low checkpoint. Snap. So low checkpoint. 3 and 3 gigabytes. Let's stop this. Let's rerun. Hit F5. Remove this, hit F5. Why is this not moving? Come on, do something. Okay. It keeps getting stuck because I'm debugging. Debugging with multiple processes, you have to be smart. Sometimes it gets stuck unless you advance the other one sufficiently close to the first one. Okay, here we are. Trainer. Let's go. Hit F5. Load the checkpoints. Let's go here. Enter here. Enter here. Let's go. Suffix. Enter. Join. First launch. No. In that case, okay, this one, we're calling the load. And we get the extra state. And same here. Okay, this one bumps it up. Load checkpoint. Apparently this one is actually loading the models to the GPU. Okay, I'm slowly getting a understanding of why I'm getting the amount of VRAM usage I'm seeing. One is OBS, sets the baseline. The second one was the all reduce, I guess some gradient buckets and stuff. The third one is obviously the load checkpoint, which makes sense. Out of all of these, that's the most intuitive one. Let's disable all breakpoints except for this one. And now let's run the train again, so we can debug that one in particular. After this, I can write a tutorial for new joiners. Okay, let's go. Let's enter here, load checkpoint. Let's see. Preparing to load the checkpoint. Should be load on all ranks. True. Load checkpoint on all DP ranks. If it's FSDP, loading checkpoint shards on all of the ranks. And what's the actual path? True. False, false, false. Load the checkpoint to CPU. And then, do we ever push it? Broadcast, let's see. File name. Aha, nice. So shard 1. Save directory. Save directory. Okay, model checkpoint shard 0, shard 1. Load on all the ranks, true. Let's see what this does. Get the local path. Okay. Shared path. Replication count. Get paths to load. Again, that's the same one. Okay. Load to CPU. What's this? This is in fairsec. Again, we just do load and we map to CPU. This one should not bump up my memory usage. And it did not. Okay. And then additionally, if common FP16, then we go through the model. Oh, nice, 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 nice. Okay. That's where it has the number of parameters. And then okay. No, 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 no. Why did I go there? Ah, I messed up. I wanted to stop there. Let's go here. I think they got stuck again. I messed up because I went over this one. No, actually it worked. So we are loading the 0th one to CPU as well. Okay. Let's continue. Data parallel world size. So does this mean we're duplicating the model? Because my understanding was we are sharding the model, we're doing the model parallelism, but I might have made a mistake somewhere. Let's go. Set the number of updates. Wait. What happened? How did I end up with 4 megabytes all of a sudden there? When did we load this? Guys, this is terrible to debug and inspect. Yeah, I just have to start this over again. Fuck it. Let's stop this. It keeps creeping up somewhere. Somehow I get from some of the lines, I somehow get more VRAM being used. How? How does that happen? I have no idea. Let's see. Let's enter. Load checkpoint. Hit F5. Grab the second one. Hit F5. Okay, they're both now at the state after the, so 5 and 2. That's the state after the all reduce and OBS. Let's see. Where does this creep in? It did not creep in here. It did not creep in here. Let's go to the second process. It did not creep in here. Okay, then where? Let's go back to the second process. Nothing happens. All good. Okay, we're here. Model set the model updates. Okay, this one seems to bump it up a bit. Yes, this one adds something to the model. Set number of updates. It bumps it up by like 400 megabytes or something, this one. Why? State from trainer to pass along to model at every update. Apply what? Crazy stuff. I'm not sure what it does. Set number of updates. Is there any definition of what that does? Transformer. Decatron. Okay, I'm not sure. Let's continue. Let me note that. So set number of updates. Line 646 in trainer.py. trainer.py bumps up memory usage by additional 400 megabytes. Just keeps on bloating up. And then let's see here, model, load the state dictionary. This might, okay, this might explode the, yes, this one bumped it up by additional 3 gigabytes or something. So let's put a breakpoint here. Let's disable all of the breakpoints. Let's stop the run. And let's just enable this one. Just this one. Train. Let's go. We are getting closer to understanding the decomposition of the memory usage. Super useful. I'd love if we were a bit faster, but unfortunately that's life. Okay, let's see here. This one was done, so let me continue. How many do we have? How many do we have here? 281, which makes sense. 271 plus these ones are, we have 279 plus 2 directions for validation. And then if we hit run here, let's quickly see, this makes sense. Okay, we dedupe job 16 jobs here, and then we can run this further. Okay, let's hit run. Output directory is okay. We can just let this run in the background. And we can continue. Okay, my only fear there was whether it will work for Flores. Let's just see quickly. Process data new. Retrieve data. Train. Validation. Nice. It worked. That's amazing. Validation worked. And we just have all of these files dumped here. Nice. Progress, guys. Progress. Let's see now. Okay, both are here. Load state dictionary. This is the this is from the FSDP. Let's do F1. Okay, we are here. Diffuse sharded state. if it's not an instance of a dummy process, we grab the state dictionary, which is currently empty, process group and CCL, broadcast the object, okay, and enter here, enter here. Again, this one contains, the other one was empty, but this one contains, okay, so we are definitely, looks like we're doing data parallel degree 2. So we are, that's why we are bumping up the, using more memory than we need. That actually explains everything, because I expected roughly, actually not, it's still too much VRAM. 20 something gigabytes is too much for this small of a model. State dictionary, encoder, embed tokens, embed positions, bunch of layers, ton of layers, and then decoder layers. So this is the whole model. And we broadcast it. So once I do this, it goes up. And then we load the state dictionary. Strict is set to true. Load the dictionary. Where is the second one? Second one is still here. Enter. Is root none? Then it's uninitialized. Load the state dictionary with summon full parameters. Now we're in fair scale. Okay. Let's enter here. Context manager. We can exit this one. Summon. Delete. Try. Okay, let's see what is this. Summon full. Okay, summon full. If we curse, enter the context. This one is synchronize. Rebuild the full parameters. Okay. And then okay, rebuild the full parameters is the one where we do gather all shards. Update P data. Okay, now we're deep in fair scale. Let's continue. Module unflattened params. And then yield. Stack close. Free the storage. Use FP32 param shared. Idle. Return false. Go back here. And we exit the summon. Okay. Reset lazy init. Exit here. Exit here. Okay. So this definitely requires a bit more cognitive capacity than what I have at the end of the day right now. So what I'm gonna do is put a to-do for tomorrow to understand a bit better here what's going on. But I think we have an answer, and that's that we have data parallel degree 2. That's why we are using so much memory. Line, what is it, 677 in load in trainer pi. Load checkpoint function. Step into it and analyze. But for now, by the end of this stream, let me just quickly note exactly how much this pumps up the consumption. So let's stop this. Let's go to training again, rerun. Okay, so we are at, let me show you, 2.7 and 5.7. After we run this, so we were at 5.7 and 2.7. Now we are at 8.7 and 5.7. So 3 gigabytes each. It was 5.7 and 2.7. Now it's 8.7 and 5.7. So roughly 3 gigabytes, roughly 2.8. Right? 5.7 to this, roughly 3 gigabytes. 2.9. Here it was 2.7. If we add 3, that's 5.7, a bit less, 2.9 gigabytes roughly. Okay, this one bumps it up by additional 2.9 gigabytes. And we're here. Let's continue and see whether we have any other. So 8.7, 5.7 roughly. Build the optimizer. Will this do something? Looking good. Scheduler shouldn't bump it up too much, if anything. Log. Load state dictionary. This will likely also bump up stuff. Let's see. So 8757, let's say. Nothing changed. Because what? Okay, let's go and grab the second one. Let's come to here. Run. Nothing. And set number of updates. This one might change something. Nope. Okay. Store EMA. Nope, we're done here. We exit here. Same with this guy. And we exit. So that was the load checkpoint. Now we grab, will this change anything? Get the train iterator. Nope. Load. Okay. And we are out. We are back in the main. We're back in the main 5.7 and 8.7 roughly. Still. And then there is a train step. Okay. So let's see here. Where does the memory increase? Progress bar. Enter here. Okay. Nothing changes. Okay, let's see once we start loading the data. Train step. Set model to train. Criterion to train. 0 grad. Log. Okay, prepare the sample should bump it up because this is moving to CUDA. Samples have around 2000 tokens. Yes, sir, almost 2000 tokens. Prepare. Almost nothing happened there. And then there is the train step. So now with all of the computations of activations and gradients, we're expecting, so currently we have model parameters and optimizer state somewhere in memory, I guess. Let me think, 3 gigabytes. If we have 600 million, that's like around 5 bytes per parameter. Because we're running efficient version of Atom, fused Atom, it will definitely not use 12 bytes per parameter. It's going to use more likely, well, 4 plus 2 and 2. It can be better than, I think, 8. That still doesn't explain these numbers. Train. We enter here. We enter here. We run the forward pass. Okay. Still 8757. Okay. Now the forward pass. So this is where I expect to get again activations. Yes. So it was 5.7, now it's 6.7. So we get plus 1 gigabyte from Okay. Now at 6.7 gigabytes for the GPU without OBS for streaming. Now let's go with this one. Begin the epoch. 5787. Let's go to the train step. Blah, blah, blah. 0 grad. Go all the way to here. And the train step. I should have put a breakpoint, oops, instead of having to step and potentially make a mistake. So 5767 criterion, forward pass, do a forward pass. It's 8.5 now. 8.5 to 12.6. 8.5. 8.5 to 12.6. 4 gigabyte increase. Once the second hits the forward pass, we get plus 4 gigabytes increase. Plus 1 gigabyte on the other one. Because it went from, we were 6.7, now it's also 7.7. So for some reason, this forward step added 4 gigabytes to one GPU and 1 gigabyte to the other one. That's wicked. So now compute loss. Let's go compute loss. And just step over. Again, we are now 7.7 and 12.7. 7.7 and 12.7. 7.12. Now it's 14.5. Okay, so that's additional 12.7, 14.7 would be 2 minus, so 1.7 gigabytes roughly. 1.7 after compute loss, the one with OBS gets plus 1.7 gigabytes. And then let's go with the second one. Let's open up the second one. So again, we are 14.595. And now, so it was 9.5, now it's 11.2. So that's again 1.7 gigabyte increase. Okay. Now let's go. So now we are at 14.5 and 11.5. 14.5, 11.5. And now, so that means we computed the loss, but now we're about to compute the gradient. Why did loss give us so much? Huh, interesting. And then backward. Now I'm expecting a lot of increase here. Let's go here, let's exit. Let's go to the backward. 14.5, 11.3. Let me just note that down. We're now at 14.5 and 11.3. Once we step over, it bumps up to 18. And the second one, okay, so we went to 18.2, 14.7. 18.2 and 14.7 after the backward pass. That means roughly 4 gigabytes for one, and around also for almost 4 gigabytes for the second one, a bit less, 4.5. Do those numbers make sense? 4 gigabytes for 650 million parameters. Like, even if it was 4 bytes for each gradient, that's still not, that's like around 2 gigabytes. Okay, let's return, delete. So 18.2, 14.7. Let's see. And then gradient collect. 18.2, 14.7 still there. Let's take the second one. Let's continue. Let's go here. Okay. Let's grab the second one. And we are done. 18.2, 14.7. Okay, let's see here. Let's see what's going on. Logging, profiler. Okay, all reduced gradients. Let's go and grab the second one. And nothing changes yet. Multiply the gradients, nothing. Clip the norm. Let's grab the second one. Let's go. Multiply the gradients. 14.7, 18.2, same here. Clip the gradients, nothing changes. If it's not TPU, then do some checks. Okay. And finally, optimizer step. Nothing changes there. Let's grab the second one. Let's go here. Let's step over. And then debug stuff. Let's see, set. Okay, drop to 16.5. Dropped. Not really, it increased to 16.5. 18.2, 16.5. Okay. Sorry, Robert, we'll reply in a second. Let me just go through this. Log the stats. 18.2, 16.5. 18.2, 16.5. And let's exit. Train step. That's it. Validate and save. This should skip. And that's it. Now we enter the second step. Let's just disable everything and see what happens for the second step. Let's get to here. Okay, let's return back and hit F5. Okay, second step is over. Hit F5. Second step. Okay. Wow. So something bumped it up to 24 and 22 after a couple of times. So like literally at the very edge, 24 and 22.5. Why? Let's hit one more F5, 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 F5. Let's just let it run. Let it just run. Now it's 23 and 22. 23 and 18, 20. Okay. I'm gonna stop it now. I think we're done for today, guys. This was super heavy session, but very, very interesting and important. Tomorrow we're gonna write in the morning the list for new joiners. I wanted to do it tonight, but this took a lot of time, more than I thought, so I had to focus and wrap it up. I'll still need to do some exploration, but I get a much better understanding of what's going on. We read the FSDP in this stream. We actually went through the nitty-gritty details of the code, so that was super helpful. And yeah, so question from Robert: does the model have recursive functions? I mean, what does it mean for a model to have recursive functions? You can define the model in a recursive way if you want, but like usually you don't do that. You just define it in an iterative way. You create a for loop and then you build transformer layers, etc., etc. But you can always, recursive functions are strictly more powerful. You can always like structure the recursive function in such a way that it looks like an iterative function, but I think that the opposite direction is not actually necessarily possible. So you can have recursive functions that you cannot model with a finite number of lines using an iterative code. Okay, guys, that was a bit more of a philosophical reply there. Catch you tomorrow. Let's continue, and hopefully the Stopes is also going to progress. We're currently binarizing the data, so let's see how that goes, and I'm going to report tomorrow. Cheers, guys. Have a nice evening. Have a nice day wherever you are, and until tomorrow. Bye-bye.